F324 January 12 question 4. So here we've got our acid anhydrides. You can see I've been doing some doodling. The chemist prepares an ester of propan-2-ol by reacting with what's this? This is propan-2-ol, isn't it? With ethanoic anhydride. Then you've got structural formulas here, and this is what nasty about this question is using structural formulae. Write an equation for the reaction of propan-2-ol and ethanoic anhydride. So obviously it is all there in front of you. I'm just going to try and walk through a little bit of, firstly, how I've drawn my structural formula, because I suggest you might not want to go straight into structural formula for this. So we've got here our structural formula for the alcohol propan-2-ol. Notice the way I've sort of changed the arrangement of it here so that my OH group is free to demonstrate how it's going to bond with the ester. But we've got here that CH3, which is this CH3 here. This carbon here is this one there, and that's connected to that H. And let's change colour. That H then is this H here. I've also got my OH group, and then my CH3 is this part up there. That then added to my acid anhydride. Notice the way that this acid anhydride is drawn in structural formula here. This section, let's just highlight the whole molecule, shall I? This section here is, of course, this bit here and this bit here, so times 2, with that oxygen in the middle being that one in the middle. I've drawn out my acid anhydride slightly oddly, just so I can take the pieces and make it more clear what is happening. So to react your acid anhydride, it's the H from the alcohol that's being removed, and it's the portion of the molecule that does not keep its oxygen that is going to bond to form the ester link. So I've tried to color code this. When it reacts, I make my ester with the alcohol notice lost its H. The acid anhydride forms the bond there to make the ester, and I'm left with the rest of my acid anhydride, which bonds with that hydrogen off the alcohol to form my carboxylic acid. No problem drawing my carboxylic acid as a structural formula, but just have a look at the way I've drawn this ester. So I've got my CH3 here, which is that CH3 there. I've got this carbon in the center, which is bonded to that C, which is this part here. I've got my CH3 on top there, which is that part there and that part there, and then I think from there it's fairly clear that this O corresponds to that O. We've got a C double bond O, and we finish off with the CH3. I suggest with that question, if you're not confident with structural formula, you draw it out displayed first, and you check that everything is okay afterwards. Part B, a sample contains a mixture of 2 esters contaminated by an alkane and an alcohol. We're going to use gas chromatography to try and sort out this problem. The column in the gas chromatograph contains a liquid alkane, which acts as the stationary phase. So here we've got a liquid stationary phase. How does liquid stationary phase separate the organic compounds in a mixture? We've got by solubility, and I would add to that it's not changed my pen. Here we go. Oh, it is relative can see why I do these things in advance, can't you, after that? Right, so relative solubility. Then, the next question suggests how well these four compounds would be separated using the alkane stationary phase. So just to go back and see, we've got a mixture containing two esters. I've lost my an alkane and an alcohol. So two esters, an alkane and an alcohol. So suggest how well these four compounds would be separated. In your answer, include indication of length of retention time. So I think that's what it wants you to say, something about the length of retention time. So I've got here that the esters would have, I've lost my cursor completely here, so I apologize. Oh, here we go. The esters would have similar retention times, similar molecules, similar retention times. So as they have a similar structure, similar solubility. Then for the final part, the alcohol, because it doesn't have a great affinity with the stationary phase, because you've got an alkane stationary phase. Alkanes form van der Waals forces. Alcohols, they've got that OH group, so they're polar molecules, they'll form hydrogen bonds. So you've not got a great solubility between an alcohol and an alkane, whereas an alkane and an alkane are clearly going to be very soluble, they both got the same intermolecular forces. So the alcohol would have a short retention time. The alkane, because it's got a great affinity for that stationary phase, it would dissolve in that stationary phase. It would hang around much longer in the stationary phase, and so it would take longer to come through the chromatography column. Okay, it's the final part of this question, part 4C. We've got gas chromatography and other techniques used for analysis. Here we've got one of the esters from the previous part of the question that's being analysed in more detail. And we've got the elemental analysis, so you're going to try and work out the empirical formula. Then I apologise, I've tried to preempt myself here. This is supposed to go with the proton NMR, and I don't know what's happened, so I'm just going to pretend that it's not there for a minute. Please excuse me. What's key to this mass spec is this tiny little point here, 144, which we'll come back to. What I want to concentrate on is just looking at how the NMR works out. So you're going to need to use analysis, and I think we're happy with that. I'll give the answer to that in a moment. The mass spec, again, there's this tiny little peak there which gave the M+ peak, the MR of that molecule. Generally you need to use one of these fragments in the question as well. We'll have a look at that when we go over the page as well. But what I want to concentrate on now is the NMR. I don't know how that slipped out of the way. Hopefully my pen's going to work. We'll be able to work this out. So again, it's all set out over the page. I just want to sort of draw up what's going on this page and see if we can put things together before we go and do all the big write-up. So here at about 0.9, with an area of 9, we've got an RCH. Now it's a singlet, so there's no adjacent carbons. So I'm going to suggest at this point that that is CH3, CH3, CH3. So I've got an area of 9, so 9 carbons in the same environment attached to a carbon that has no hydrogens on it. So it stays a singlet, and I've got an area of 3, assuming they're all, an area of 9, assuming they're all in the same environment, which is what it must be if it's an RCH. There can't be anything else but those 3 CH3 groups. Then at about 0.1, 1.3 or 1.2, 1.3, you've got a triplet. It's again in the RCH region, and this one is going to be a CH3 because it's got an area of 3. I'm thinking because it's got let's do that. Because it's a triplet, I'm thinking that next to it I've got CH2. So I know that my area is 3, so I've got CH3. It's a triplet, so I'm thinking there's a CH2 next to it, because remember n+1 rule, you've got 2 adjacents plus the actual environment itself. Then this third peak here, about 2.2, 2.3, that is going to be the environment of an H connected to a carbon that's connected to a C double bond O. And this one, it looks it's going to have an area of 2, so it's 2 H's connected to a C double bond O. And next door to it, it has, because it's just a singlet, it has no adjacent carbons. So here on this carbon, I can't have any hydrogen, sorry. I can't have any hydrogens there. I haven't got any hydrogens there. So it's an area of 2, but with nothing adjacent to it. Then for my final fragment, I've got an area of 2 again. This is a HCO. It's a nice O, isn't it? And it's got an area of 2, so I can have it as CH bonded to that O. And next door to it, because it's a quartet, I must have CH3. So that's a quartet, so it means that I've got 3 adjacent plus the area 2 itself of that particular chemical shift, your CO chemical shift. Now, from here, that looks like then it's the end of the molecule. It's got a CH3, it's terminating, it goes to my O. I know it's an ester. The other side of my ester, I've got the C double bond O, which must be connected to this part of the molecule. Then I've got a C with 2 H's and a C with no hydrogens on it, which I'm hoping will be this carbon here, so that I can attach this carbon, or I'm saying that that carbon, now I've lost me, here we go, I'm saying that that carbon is the same as that one, so that one is linked, I've lost my cursor again, here we go, this one is linked to that one, so I'm thinking those two pieces go together, and then that C double bond O links to this O, which will link to these two. I've got evidence for this being correct from here, because again I've got a CH3 at the end here, which is adjacent to a CH2, which is this CH2 here. So hopefully that's how all my pieces will fit together. Let's just quickly draw that out. Hopefully the pen will let me. So let's do it this way. So I've got a C at the end with my 3. Oh no, it's not going to let me do it, is it? That's yeah, maybe we'll turn over the page and we'll have a look at that one. So over the page, then we'll go through our analysis, and then I'll have a look at the shape of the molecule. So analysis from the question, and notice that we've got use the results to identify the ester, showing all your reasoning. So we've got the analysis here, we've got the percentage compositions, dividing by the MR, then dividing through by the smallest. We've got some nice numbers here, so we've got 4, 8 and 1, which gives us our empirical formula. From the mass spec, we've got the M plus at 144, and so we need to show clearly that we've got the molecular formula as C8H16O2. You compare your empirical formula to your molecular formula, and then you scale it as necessary. So here I've done 144 over 72, and then said, right, well, I'm going to have to times my empirical formula by 2 to get my molecular formula. Then going on then to look at each of these peaks, we've already talked at them. This is how you need to set them out really. So peak at delta equals 0.9 shows 9 protons, so 3 CH3s in the same environment as it has an area of 9. So you're essentially putting down everything. Chemical shift, you're saying it's 3 CH3s and that they must be in the same environment. Get all of these ideas down, because I know they're in your heads. Get them onto the paper. So as it has an area of 9. Peak at delta 1.3, and we can say that we split into a triplet with an area of 3. So that shows it's a CH3 with 2 adjacent protons or 2 adjacent hydrogens. Notice you've got QWC there for the spelling of triplet. Then you've got the peak at 2.2, which is a singlet, so no adjacents, hydrogens, and you've got that particular, you've got a CH2C double bond O, as I drew on the spectra earlier on. Then you've got a peak at 4.2, split into a quartet, so 3 H's on the adjacent carbon shows an H pointing to a CO. So that's how I'd write it all out. The molecule as it looks, we've got our 3 methyls connected to our carbon with no adjacents, connected to a CH2, which is connected to the C double bond O, and the O connected to CH2CH3. I will go back and see if I can piece that together from the from what I've scribbled on my. Let's see if the pen's behaving itself again. So going back, trying second attempt. I'm going to start here. So I've got a C with a CH3, a CH3, and a CH3. Now I thought that that was connected with this one here, which has got a CH2 going to a C double bond O. So that's the first half of my molecule. I worked out that I had a 9, so I had 3 of those. This peak, I knew that it was an H connected to a carbon, connected to the carbon with the C double bond. I worked out that it had 2 from the area, and it was connected to something with no adjacent hydrogens, because I've got that singlet there. So those two fit together nicely. Then I know this is going to be my O because I've been told it's an ester. So I'm looking straight here and I've got a C from the area of 2. I know that's the case. The splitting is a quartet, so I know that must be a CH3 adjacent to it. And that's confirmed here where I had an RCH2, an RCH3 with an adjacent CH2. So they match up with each other. So there you are, that's the final question on that paper.